Kia ora, no mai haere mai. This is the 3D coastal mapping webinar. Welcome. We're going to speak to you today about coastal mapping, and our presenters are Stuart, Caie and Alysha Johnson. Let's start with a karakia to get us going. Whaia te matauranga, kia marama, kia tupu, kia tiaki ngā whenua, ngā moana, ngā arawai, kia whai taki ngā mahi katoa, aroha atu, aroha mai, tātou ia tātou, toi te kupu, toi te mana, toi tu te whenua, haumi e, hui e, taiki e. Welcome. We're just going to go over some housekeeping for you today for this webinar. Okay, so in terms of questions, we welcome your questions. We're going to answer your questions at the end of this webinar. At the top of the screen, you should see a Q&A button. So if you click on that, that opens the questions and answers tab, and you can put your questions there. And at the end of this webinar, we'll answer those for you. If we can't answer all of them in this webinar, what we're going to do is we're going to gather all those questions and reply to them and send them in an email. And in that email will also be a link to the recording of this webinar. So this webinar is being recorded, and you'll see that in the link. Okay, so let's get started. We've got a few people now joining us, so we'll start with Stuart. Stuart, thank you.
Thank you, Amanda, and kia ora koutou through all those online. Good to see a group of people now joining. Interested to hear about a little bit of update to our program, 3D coastal mapping. So just a bit of an overview of what we're going to take you through today. We'll talk about an update on the journey so far. I'll hand over to my colleague Alysha, who will look at some of the insights and what we've captured, have a look at some of the data. And then I'll talk a little bit about the benefits from the project and the for New Zealand, and then just briefly touch on what we're doing next. So just a quick reminder about why we are doing the program. The project will significantly improve baseline data upon which resilience to coastal hazards and climate change impacts can be assessed and mitigated. It'll provide improved data to identify coastal areas of significant risk of flooding, tsunami and inundation, and help communities, local and central government to plan and adapt to climate change induced sea level rise and more frequent storm surges. And then just touching that, actually this program was identified as a future work in the Ministry for Environment's Aotearoa New Zealand's first National Adaptation Plan, published in 2022. So just to go over the exposure to sea level rise and some of the stats and drawing on reports and studies carried out over recent years. So in 2019, NIWA, now Science New Zealand, prepared a report for the Deep South Challenge. And the study described New Zealand's exposure to 1% annual exceedance probability of coastal flood inundation under present and future higher sea level rise. Bit of a mouthful, but what that actually means that each year there is a 1% chance of a coastal flooding event occurring due to extreme sea levels influenced by a combination of tide, storm surge, mean sea level anomalies and wave setup. The study used available high resolution topographic LiDAR elevation data and a slightly coarser satellite derived elevation model where there was no LiDAR coverage. The study then developed national and regional level risk exposure to different amounts of sea level rise. So this figure here shows in terms of a 0.6 meter rise and also a 1.2 increase in sea level rise. So as well as an impact on infrastructure and rebuild costs, property insurance and reinsurance will become an issue. The 2020 report on insurance retreat, which occurs when insurers decline coverage based upon a property's exposure to an escalating hazard such as sea level rise. And this study shows that at least 10,000 homes in the Wellington, Christchurch, Auckland and Dunedin regions full insurance retreat is likely to occur by 2050. And also in the news, we're seeing from the media more and more coverage on the impact of sea level rise, and also some hopefully good news stories about the program of work and how it is feeding into these issues. And it's not just economic impact, I think it's worth noting, but also that real impact on areas of cultural significance, in particular the White Owl Bar. So a reminder of the targeted areas that we're mapping, as indicated here on the map in orange, and again that the scope of the mapping extends approximately 200 meters inland of the coastline and out to 25-meter water depth, or as much as the LiDAR can achieve given some of the environmental conditions. So over the first season that ran from July through to May, we were able to cover approximately 20% of the scope. That's been complete, so that's around about 2,000 square kilometres. So when I say complete, there are still some gaps within the LiDAR areas, but these have been caused by continued turbidity or suspended sediment, which affects how deep the LiDAR can penetrate into the water. And even with a number of reflights to try to fill in the gaps, if there was continued turbidity, then there's really no point in carrying on with collecting with the LiDAR. And as the weather wasn't that great last summer, the suppliers moved around the Motu, making the most of the good weather where it became available. Hence, there are some areas that have been started, and those are indicated here in this image as in progress. The other stream of work with coastal mapping was to install new or upgrade global navigation satellite systems, or a GNSS receiver, at existing tide gauges. So in addition to the tide gauges, they're being calibrated and then connected to a physical control point, which is in terms of a national vertical datum, so the New Zealand vertical datum 2016. And similarly, the GNSS receivers, they are connected to the same control points, so that both data sets can be brought together to determine the relative rise in sea level. So basically, the impact of sea level rise isn't as great in areas where the land is rising at a faster rate than sea level is rising. So I'll hand over to Alysha, who is working on the program. She's been validating the data as it's been coming in and getting it pushed out to be published. Alysha will take you through some of the examples of the data and the process we follow just to check it over. So over to you, Alysha.
Tēnā koutou katoa. My name is Dr. Alysha Johnson. I am a geospatial specialist here at Toituta Whenua. And as Stuart said, I'm going to talk to you about what we do with the data once we get it and really showcase some of the awesome data that's come through so far. And the first thing I'd like to draw your attention to is the data that we actually already have online. So last year we did our trial data in Tauranga and in Invercargill, and these two data sets are now available on the LINS data service. And you can find these under New Zealand Coastal Elevation. There's a couple of different data sets that are available. This includes a 1 meter digital elevation model, or DEM, the survey index, which has metadata, and hillshades as well that you can see showcased to the right. And this is the best place to go back to new data. So when our new data is ready to be released, we'll update this layer and you'll see new patches of the country become filled in. So our data has been coming in from the suppliers since July, and we expect it to continue this season through October and November. And once those are approved from our QA, we will pop them online. So what is our QA? There's a couple of things we check to make sure that the data is as good quality as it can be. We're very interested in the accuracy of the data. So if it's accurate vertically and if it's accurate horizontally. And we check that against our best known comparisons, such as topographic LiDAR or our deep water multi-beam bathymetry. We have a look at how dense the point clouds from the LiDAR is, And we also have a look at the classification of those points. So is a point that is the seafloor classified as the seafloor? Is a point that is the ground classified as the ground? Are points that are noisy or erroneous correctly classified? We have a look at the DEM when it's been generated. We make sure no artifacts have been accidentally put in that creation process. And we have a look to make sure that there are no data voids, so no big gaps in the data. Now, this is a bit challenging with the nature of LiDAR, bathymetric LiDAR data, because we can only work to a certain depth, and we might have molecules and particles in the water that make it turbid and make it hard for the light to penetrate through it. So we might get a few gaps, but what we're doing is keeping that to a minimum. And ideally, we're going to get a seamless surface that runs all the way from the coast through the intertidal area and out into the seafloor. The first data set I want to showcase to you is Doubtless Bay and Monganui Harbour. Now, this was flown in March this year, and 72 kilometres squared of data was collected. This data goes to 20 meters deep, which is quite exciting. And what I'm going to do is talk you through some cool things of interest we found in the data. If you have a look in box A, oh, sorry, go back one, Stuart. If you have a look in box A, you can see northern Doubtless Bay, and there's a couple of little things sticking out in the blue of the seafloor. Keep those in your head because I'm going to refer to them on the next slide. And in box B, we see a cool river coming out with a bit of an estuary and a sand spit forming as well. So our northern two ones, the top two images, think back to that northern area of Doubtless Bay. There are other ways we can view it to see what else this information tells us. So we can have a look at it in 3D. This is elevation data after all. And you can see the rocks which have formed both in the seafloor and then around the headland stick out really well. And we can use another type of data called intensity or reflectance to view that even better. So this is a measure of how strong a signal from the LiDAR is. If the signal is really strong, it probably means it's hit something hard like a rock or consolidated sediment. If it's really weak, then it's hit something like soft sand. And so if you have a look at the image in the top right, we can see those rocks are showcased really well with dark colors. We can also see some like dappled features in the middle there, and that's probably some organization and structure from the sand. And then we can also see the surf zone where the sand and the waves are moving in and out, which is a cool temporal snapshot. An important thing to note regarding intensity data is it's a relative measure. So this data shouldn't be compared to other data sets. It's only relevant within itself. And then lastly, we can see a cool 3D view of Monganui Harbour looking about 7 kilometres up the harbour, which is very cool data coverage. The next location to showcase here is Pepin Island and Rotorua in Cable Bay, which is found in the Tasman Nelson region in the South Island. And this covered a 35 kilometres squared of data was collected up to a depth of 27 metres, which is a really cool depth to get to. We can see in A in the top right-hand corner, again, this is our intensity data, and this is from Rotorua Cable Bay. And you can see if we look inside the bay, there's areas where it's a little bit darker. And so this is likely some form of rock or sand shoaling, which is about 0.5 metre to 2 metres shallower than the surrounding seafloor. Behind it, we can see that dark area. That's a muddy estuarine area. So quite cool tool to use to help us look at the seafloor. We have a look at B as well. We can see another side of that estuary, and here you can see some 1 metre deep channels flowing out into the bay itself. One thing I really like about this data is that it's seamless. So this fly through, you can see how it goes all the way from the coast down into the seafloor quite continuously as we fly across Delaware Bay, round behind Pepin Island, and then out looking into Rotorua Cable Bay as well. Awesome. I will hand it back to Stuart.
Well, thanks. Thanks, Alysha. Yeah, so it's really exciting to actually see the data now. It's been quite a bit of a build-up to where we are now. So actually seeing some of the data coming in, it's really exciting. Some of the really interesting features that are coming out, and really understanding, you know, how will this data be of use and what the benefits that it's going to bring. which brings me on to exactly that. So we'll have a look at some of the benefits that New Zealand. So at the beginning of the programme, a number of sectors were identified which could benefit from the data that we were collecting, and they're shown on the screen there. So we talk about hazard and risk modelling, feeding into identifying areas for economic development, infrastructure resilience, adaptation planning, managing the environment and ecosystem, and also touching on safety of life. So although this data is being collected for a particular purpose, there are other ways that this data can be used and other benefits that it can be put to. So as mentioned earlier, the programme will significantly improve baseline data upon which resilience to coastal hazards and climate change impacts can be assessed and mitigated. So being able to accurately model the impacts and identify locations is key to providing those that need it the information necessary to make decisions on appropriate mitigation measures. As we're in the early stages of receiving the data, we don't necessarily have use cases based upon the data yet. So this is an example taken from topographic LiDAR just to demonstrate what we're anticipating seeing. So this image shows the elevation model constructed from topographic contours at intervals of 20 meters. So you can see it's quite blurry looking, so not very well defined. But now where so much more definition and detail is revealed with the LiDAR derived elevation model. So taking the high density LiDAR data and producing a 1 meter DEM from this, and then overlaying on top of that the surface model, which includes vegetation, bridges and buildings. So building a very detailed image representation of the land. So now, so how does this improve our understanding of, say, the effects of sea level rise or storm surge? So here's an example of inundation modelling at Sumner Head using an elevation model created from the 20-metre contours overlaid with some aerial imagery. This suggests that it's only those properties close to the water that will be affected by a rise of 2 to 4 metres. However, if we overlay the high resolution data, it really shows that there's far more properties are affected with an inundation of less than 2 meters. So this example shows one component of elevation, the land. So what's missing in here is the shape of the seafloor in front of that area. Understanding this component provides a fuller picture of the shape of the land and how it may affect the run-up of waves and impacting the level of inundation. So just some examples of how the data could be enabling the accurate modelling. On the left-hand side there is the coastal flood layer viewer from NIWA. The map provides a modelled representation of New Zealand's 1% annual accedence probability of that extreme sea level flooding under current conditions. And then you're able to step through to a 2 metre sea level rise, representing the inundation. The middle image is taken from the NZ sea rise, Takiwa, and shows sea level rise and vertical land movement incorporated under potential climate change scenarios. And on the right-hand side, a study in Hawke's Bay showing the extent of coastal inundation probabilities and some of the estimated losses. So again, this data that we are collecting, although we don't necessarily have it at the moment, is obviously going to be feeding into these particular examples, and it'll be great to see these things run again with updated data. So the importance of modelling, what is it? And really try to understand and quantify the impact of events on the population, infrastructure, and that financial cost. Improved elevation data is key input into hazard modelling that enables a better planning and response by councils, particularly for floods, landslides, coastline inundation, and sea level rise. Accurate risk assessment informs better decisions around mitigations and adaptations, such as building defences, response plans, insurance underwriting, and secure resilience. The National Hazard Commission is transitioning its loss modelling to Riskscape with the intention of expanding the other hazards that it covers to include tsunamis. So being able to identify and quantify the impact of events leads to improved decision making relating to economic development, adaptation planning, infrastructure resilience, managing the environment and ecosystems, and as mentioned, safety of life. So with 65% of the population living close to the coastline, then obviously there's a big impact on the population, along with buildings and the rebuild cost for many of those properties. So as an island nation, we rely heavily on our marine environment for trade and tourism, and in line with global figures, 99% of goods, that's by volume, travel by sea to from New Zealand, and this contributes around about $7 billion to the New Zealand economy, so pretty significant. And for tourism, this contributes nearly $29 billion to the economy. That was in 2024. And supports over 303,000 jobs within that industry. So similarly for New Zealand's aquaculture industry, it has a current annual revenue of $750 million plus, and with a projected annual review by 2033 of $3 billion. And again, this supports a significant number of jobs within the New Zealand communities. So adaptation planning, this really involves the developing strategies to manage the risks and impacts of climate change. It focuses on preparing for and adjusting to the effects of climate change, rather than solely trying to prevent them. And this includes assessing vulnerabilities, identifying adaptation options, and implementing actions to build resilience. The first National Adaptation Plan, published in 2024, outlines the strategies to integrate climate resilience into governance, community planning, and business operations. It emphasises equitable transition and collaboration among government sectors, local councils, Māori communities, and private enterprises. And at last year's New Zealand Coastal Society conference, I was impressed by a presentation by the Christchurch City Council, where they talked about their approach to developing an adaptation plan, which sets out how they could manage the risks posed by coastal hazards and sea level rise for 6 communities in their district. The plan's actions were considered and proposed by a coastal panel of people from those communities, including local runanga, and then formally adopted by the mayor and councillors of Christchurch in March this year. This is just one example of assessing the risk and putting in place a plan to manage the impact of sea level rise. But I think really important to note here that some hard decisions will need to be made on which adaptation option is best. So in terms of infrastructure resilience, as we're well aware, many of the state highways and railway lines run along or very close to our coastline. A 2019 study by NIWA presents New Zealand's exposure, again, to this 1% annual exceedance probability to coastal flooding, inundation, under present day and future higher sea levels. The investigation estimated extreme sea level elevations at present day mean sea level around New Zealand coastline, resulting in a combination from tide, storm surge, mean sea level anomaly, and wave setup. This shows that just over 1,400 kilometres of roads, 3,180 kilometres of 3 water infrastructure, so pipelines, that are currently exposed to present day extreme coastal flooding. As well as 72,000 people and 50,000 buildings. And with the 0.6 metre rise in sea level, these numbers increased to over 132,000 people, almost 94,000 buildings, 5,500 kilometres of pipeline, and there was another value in there, 142 kilometres of railway line. So big numbers, big impact on our key infrastructure. that can easily cut off communities from resource and response activities. So the last sector I'll touch on is the management of marine environment and ecosystem, which could benefit from the programme's outputs. The case study in the lower right there is from Catalan, and it's the government using LiDAR data to improve management of its marine environment. This project provided accurate mapping of the seabed and geomorphology, sediment and ecology, revealing the various habitats and species and their extent of distribution. As Alysha showed us earlier with the data examples, combining bathymetry and reflectance, we're starting to get a better picture of what the seabed is made of and the impacts of wave motion. This can support the mapping of marine habitats, monitoring changes to the coastline caused by erosion and deposition, and the impact of storms on coastal ecosystems. So, and finally, a quick overview of what's happening next. We have the two suppliers. They'll be returning in a couple of months' time to carry on with the LiDAR mapping work. We still have to have discussions with them in terms of identifying and nailing down the program, but we'll certainly tap into what we learned from the last season. The trial LiDAR set is now available on the LINS data service, and as more data becomes available, then that will then get pushed out and added to that layer. So that one layer, the 1 meter coastal DEM. And as I mentioned earlier, there are some gaps in the LiDAR coverage caused by high turbidity, but what we're looking at is a program of work to infill some of those areas on a priority basis using more traditional multi-beam echo sounder surveys. We have plans for establishing an advisory group that will represent the needs of stakeholders and really ensuring that the data meets their needs and encourage uptake of the data. So it's all well and good us collecting this data, but we really do need to make it be pulled into programs of work to be able to modelling, to be able to understand the benefits of it, so we can actually show the value in the work that we're doing. And obviously, just with webinar and other communications, we're going to continue with our engagement with you, our stakeholders, on this work as we progress. So thanks for your attendance. If you've got any questions, please do push them through. What I'll do is I might just hand you back to Amanda to go over any questions, but maybe just to close us out with our karakia. Thanks very much.
Kia ora, Stuart and Alysha. We do have some questions in our Q&A section. That's the top of this meeting. You can see the Q&A button if you want to add some more. The first question I'm going to ask, and this is for Alysha, is from Benjamin Scott, and it is, during QA you check against topo LiDAR. Do you also check against ground survey data?
Yeah, that's a great question. Something I wasn't covered in the talk is actually some of the QA that our suppliers do prior to giving us the data. So they use control points, which are survey points on the ground that they will link their data to. And they will also do things called cross-line surveys. So they will fly twice over the same area and be able to do comparisons there. So we get their cross-line information, and we also get their check sites as well. And we can check that to our data too. So there's these other elements that ensure that accuracy is tied in to not only accurate on the bathymetry, but to the truth spots, if for want of a better word, on the topography as well. But it's a really good question.
Kia ora, Alysha, and there is another one here for you, and it's from Jitan Patel. Hi, Alysha, what software do you use to create the 3D fly-throughs? They look really cool.
Predominantly used for the fly-throughs ArcGIS Pro, but some of the other visuals that I showed were created in QGIS as well, which is free.
Wonderful. And our last question in our section from Laura Reid. Super exciting team. Has there been any barriers to capturing target areas with large areas of sediment or turbidity?
Yep, I can take that. Thanks, Laura. Yeah, great question. Yes, definitely. we were fully aware that the New Zealand environment is going to be quite a challenge for this technology, and we have had regular contact and meetings with our suppliers just to go through what's been achieved in coverage. And what they've built into the program is a number of hours of reflight, so they can actually go back and fill in areas and gaps, whether that's been through to equipment not working properly, or in many areas high levels of turbidity, so suspended sediment within the water, which then doesn't allow the laser light to penetrate deep down. So we go through a process of looking at the areas, understanding, are we going to get anything more if we collect more LiDAR work, or is that just wasting time and effort, and then focus efforts elsewhere? So we've gone through that conversation a few times, and in some areas, hence the program of work then to do some multi-beam work. Some of the other, not necessarily barriers, but challenges we've had, there's been a couple of seabird sanctuaries that are up around Cape Kidnappers, gannet colony, similarly down at Tairoa Heads, another gannet colony, and there are some restrictions around flying aircraft over those colonies at their breeding season. Unfortunately, breeding season coincides with the best flying season, so we're having to make decisions around flying higher or not flying at all. And obviously, if we fly higher, then it has a little bit of an impact on the data resolution and data density. So some interesting challenges in our environment, and I think the two suppliers are quite interested in and have learnt a lot, as we all have.
Stuart, we've got a few questions that have come through. This question is from Michael Campen Fordham. Will the LiDAR point clouds be publicly available via OpenTopo or similar to?
Yes, that's correct. So the point cloud data will be made available, as well as the digital elevation models. And we also have the raw data. So these systems, the LiDAR systems, capture the full waveform data file. So all that will be made available. They're large files, so they won't necessarily be pushed out through LDS. So there may be some things, or the OpenTopo, there may be other avenues that data could be made available. But certainly as data becomes available, we'll be letting people know about it.
Thank you. And the next one is from Brian Scholes. How frequently is there issues with green LiDAR not being able to get sufficient elevation data due to turbidity?
Yeah, so there's been occasions. We haven't had too much trouble around the North Island, which has been great. There's been a couple of areas there where we've maybe had some aquatic vegetation that gets in the way, but we've certainly had some more higher levels of turbidity down around the South Island. So certainly around the Otago coastline, up around Karitane and up towards Oamaru, there's been some high turbidity areas. So we're then kind of taking that on and looking at ways of infilling that data. So there are some areas. What the suppliers are doing is maybe moving on to an alternative area, waiting for the one area that has an issue with turbidity to maybe clear up, and then returning to fill in those gaps.
Thank you. Now, Derek Finn asks, is there any scope to fly critical areas missed, for example, Port Waikato?
So we have had conversations with stakeholders just to identify areas. So we are working to within our budget to be able to cover what we already have for the scope, and then certainly considering if there is anything left, anything remaining that maybe we were able to then cover off additional areas. So we're basically within our scope, we're talking about the LiDAR coverage, but also including the multi-beam surveys as well. So I think we're going to be quite tight, I think, in terms of what we're able to achieve with our funding.
Now, Nemo Thompson asks, will you be publishing any imagery that was captured during the LiDAR capture?
Yep. So along with the LiDAR, we are capturing aerial imagery. It's more of a secondary output. Our main driver and main purpose is obviously the LiDAR. But yes, there is imagery that's being collected, and that will also be made available.
From Lisa Armstrong, we've got, what is the planned time frame to complete the areas not yet started?
Okay, so the program carries on through until June 27. We hopeful that we'll have a full flying season this time round, so this summer coming, and should be able to get through quite a bit of the scope, maybe just leaving some small areas to get mopped up with the LiDAR in the final year. So that's 26, 27. So over this period of time, up to June 26, the work is a time frame for completing this work.
Now, Emily Lane is asking, in some places you said you're able to get to 20 metres in depth. How often were you able to get this deep? Presumably this is dependent on turbidity or sediment.
Yeah, absolutely, Emily. So in many areas, we've been able to get more than 20 meters, actually getting out beyond the 25-meter water depth, 27 meters in some areas. Obviously, we're very good water clarity. Yes, very much dependent on the turbidity. And what we're often seeing is even some slightly deeper areas, if there's some sound waves or troughs, then in the trough there might be a little bit of sediment that we're not actually getting, but that's beyond the 25 meters. So that's small areas, deeper than 25 meters, but obviously some turbidity hanging around in those areas.
Thanks, Stuart. Now, our last question in our Q&A box is from Joshua Sargent, and it is, how is the elevation data managed at the land-coast interface, considering differing local vertical datums?
Yeah, good question, Joshua. And vertical datums is a bit of a challenge. However, the way that we're addressing this is that all of the data that we are collecting through coastal mapping is in terms of the New Zealand vertical datum 2016. So there we're getting that continuous seamless data capture on the same data across the land and the sea. The challenge then becomes, once we want to start joining some of our existing bathymetry data that may be in a different vertical datum to this data set. So there's a piece of work going on to be able to solve that problem for us. It's not as easy as saying that. It is quite complex and involved, but that is something that we are working on.
Well, ngā mihi nui, Stuart and Alysha today. Thank you for that presentation, and thank you for everyone coming to this presentation today. So just to remind you that we'll be sending out these Q&A responses, and we'll be also sending out a link of this presentation so you can watch it in your own time or share it with your colleagues. So thank you, everyone. Now we are just going to end up with our closing karakia. Kua ia te kaupapa, ka re nā huia, ka rere nā arawai, ko mau te matauranga. Hei arahine nā mahi o toitu te whenua, kia tau te rangimari e, ki runga i a tātou katoa, haumi e, hui e, taiki e. Thank you, everyone.